Keep the grade on a spreadsheet, so you don't know I wouldn't say it's pointless, but I think yeah.
You don't have to.
Yeah.
Okay, team, go ahead and get started, please.
Good evening, everyone. We are Team AI Architects, and today we are here to present our capstone project titled AI Project Risk Reduction. Firstly, we would like to thank our professor, Dr. Rollins, for her encouragement and guidance throughout this project, and also extend our gratitude to Dr. Rasmussen for his valuable insights and suggestions. Meet the team for this project. Sharath is the Scrum Master. Harshit, who is the product owner, and the developers are Jaideep, Shashank, Abbas, and I'm Kirtana. Regarding the table of contents on what we'll be covering today, we'll start with the problem statement, like what the problem is actually about and also the importance of the problem. And then moving on to the multidimensional algorithm structure, project phases, data sets, data synthesis, and then the exploratory data analysis, and also the modeling strategies which we've used in our project, and then the visualizations, cost estimation, demo, and finally the summary and future work. Our journey for this project began with understanding why so many AI projects fail. Despite us knowing that AI has been increasingly adopted and rapidly integrated among various industries like healthcare, finance, and retail, we can see a widening gap between what AI can do and what it actually delivers. Many organizations struggle to align these AI tools with the real-world needs, which results in the high failure rates. The main problem we found, according to literature, are the poor algorithm selection and the inefficient resource allocation. These decisions prevent the AI projects to solve the domain-specific problems effectively. The aim of our project, again, will be understanding why the AI projects fail and also to reduce this risk by better decision-making frameworks. We just don't want to explain about the past failures, but also guide with the future success as well. So we developed a dashboard which will be helpful for the project managers to choose the right strategy and right model, which will be aligning with their domain needs. And in the longer run, we can also improve the return of investments and also the overall project impact as well. Coming to the importance of the problem, why is this problem important? Because this isn't just a technical problem, it's also a strategic problem. Breaking this down, we can see that the failed AI projects leads to financial losses, which can damage the stakeholders' trust, and finally, slowing down the future adoption of AI. Without a structured framework, it is difficult to predict or prevent these failures. So that's why we believe the effective risk management, along with validated frameworks, is crucial for the sustainable AI deployment. Next, my teammate Abbas will be continuing. Thank you.
Thank you, Kirtana. So, at the heart of our project is multi-dimensional algorithm structures or MAS framework. So, MAS is a structured methodology developed to to select. Sorry. So, MAS is a structured framework which is developed to guide the selection of AI algorithm structures by applying 6 key dimensions, as you can see on this slide. So here, are let me walk you through the 6 dimensions. Human in loop. So human in loop defines the input level of human involvement in decision making of an AI projects, like whether it's direct, indirect, or autonomous, and algorithm functions, which it categorize the algorithms based on the purpose, like descriptive, predictive, or assistive, and data types. It specifies the type of data used, like whether it's text, image, or audio, and data format. It identifies the whether the data is structured, unstructured, or semi-structured data, and data quality is the measures that data is stable or reliable, like it's an infrastructure which determines the computational power required, like whether it's low, medium, or high. So our project is structured into 3 main phases. Like in phase 1, we gathered the data from various sources, and in phase 2, we worked with techniques like CT GAN, which help us to build a structured synthetic data, and also we formed a MAS framework. And in phase 3, we did the data synthesis and data modeling, and then we developed a dashboard for a risk analysis. Next, I will hand it to the Harshit.
Thank you, Abbas. Regarding the data sets, throughout the project, we have come across the multiple data sets. We'll deep dive into each data sets that we have considered, and I'll let some clarity to all of you about the data sets we have chosen. The raw data set, it consists of all the AI projects with the description whether the project has been successful or failure. And the original model data set is the one which includes all the machine learning models which the AI projects in the raw data set. And the model catalog data set is the data set which we have considered from various resources and research paper articles in order to develop the new model data set. The new model dataset is the one which we have obtained from the original model dataset and the model catalog dataset by using a technique called Jaccard coefficient, which will be learned in which will be presented in the future slides by my teammates. The Likert score dataset, it consists of the project evaluation metrics such as compliances level and the cost using the standardized scale. The synthetic data, we have developed the synthetic data using a CT-Jang technique in order to in-depth analysis of our project. Yeah. For the data synthesis, we have during our project we have collected the data from various resources like literature reviews and the research articles, but we are able to collect the sparse amount of data. This is a point where we have decided to synthesize the data for the deep analysis. And we have considered a technical new technique. We have considered a technique called the CD-GAN. The main reason for choosing the CD-GAN technique is because it can handle the both numerical and the categorical data fields efficiently. The CD-GAN technique also works on the patterns of the original model data set to create the statistical similar data for the data synthesis. We have also added some of the constraints so that some constraints such as limiting machine learning models to the AI catalog and the limiting limiting model for the description for the semantics. This is a process where we have started from the raw data set to create the synthetic data set. This is the flowchart where we have described it. And this is an AI project timeline chart where the x-axis represents the timeline of the project and the y-axis represents the different AI project. Here, the red bar represents the projects that are failed, and the green one represents the projects that are succeeded, and the yellow one represents the projects that are partially succeeded. What we can observe over here is the projects which have failed are having the long time of intent, which means that because they have flaws in the execution of the project properly and inadequate data and the modeling process for the project. Yeah. From here, I'm going to hand over my mic to the Sharat.
Thank you, Harshit. Now I'll be discussing our process of selecting new models that reduce the risk of failure for the projects. So in our case, this is a 3-step process. We first start by aligning the project dataset and the model dataset to the mass attributes. So this breaks down the models by 6 distinct spheres, the mass spheres. And let's talk about the first step of the process, which is Jacquard similarity. So what does Jacquard do in our process? What it does is it finds similarity between the mass attributes, between the project dataset and the model dataset. And it performs a Jacquard index between those, and it gets a score. And the second step of this process is the semantic semantic boosting. The reason we have committed to semantic boosting is because purely relying on mass attributes won't give us the ultimate relevance for the model to be selected, which is why we have also used semantic boosting. And the way it works is it compares the model description attributes in both the project dataset and the model dataset, and it finds similar words, and it creates a mapping between those two. And this is how it occurs. And the third step of the process is scoring risks. And how do we do this? After we align the mass attributes with the model dataset and the project dataset, we then go into each category of the mass attributes, and we give them scores. For example, the data type text could have, it has the least risk compared to other categories like video and audio. And this is how we are able to, after we get the risk scores, we would have to perform a weighted equation. And we cannot just simply perform a weighted equation, a weighted average, just because assuming that all the factors affect the failure in the same way, which is why we have performed a automatic we performed the automatic weight detection by making combinations of by making 1,000 combinations, and we selected the weights that are relevant to the projects in our data set. And this is our slide for data integration. We started with our raw data set, and as I've said, we have aligned our mass attributes to the data sets, and that goes into the original data sets, which contains all the projects along with the mass attributes. We then decided to also create a Likert score data set. We decided to do this because since we gather all this data off of articles and research papers, and none of the projects disclose their actual costs, we decided to go with a Likert cost band, which can help us assess the approximate cost of the projects. And we moved from the original model datasets to new model datasets. We obtained the new models by performing Jacquard similarity and semantic boosting from the model catalog dataset. And using all this data, we pre-process and we prepare the synthetic dataset. JD will continue.
Now I'll be discussing how the new models affected the risk for mass fears. So these visualizations basically show us the change in risk for the models that are deployed and the models that are recommended for our projects and for specific spheres. So if we take algorithm function, the risk for most of the projects decrease. So if you take, say, for example, Clearview AI, for the old model, the risk is pretty high, but for the newer model, the risk is moderate. But when we come to data type, the risk remains the same for all the projects, even if the new models are implemented. Coming to data quality, the risk decreases for data quality as well. For example, if you take like Google Flu Trends, the risk is high for the older models, but it's moderate for the newer models. But the risk remains the same for data format for all the projects. Now coming to infrastructure. The risk actually increases because it also varies depending on the spheres that we just talked about. Say for Facebook trending topics, the old model had a low risk value, but then the newer model had a moderate risk value. So in this slide, I want to walk through how we were doing our Likert scoring. So basically, we had about 9 attributes that we wanted to convert into Likert scores. So the 9 key attributes that we had for our project were our mass fears, which included infrastructure, algorithm function, data type, data format, data quality, and human in the loop. And then we also had to add 3 more contextual attributes, which were scope, the daily data volume, as well as the compliance costs. So when we came up with these attributes, we also provided weights for each of these attributes. And for daily data volume, it was a numerical value and not a categorical value. So we had to apply logarithm transformation. So after we were able to get convert all the attributes, we were able to calculate the Likert score, which would range from about 1 to 7. So on this slide, the table shows us the Likert scores and then also provides us with the description and characteristics. Now my team member, Shasank, will take over.
Thank you, Jaideep. This is the brief overview of our risk analysis dashboard. This mainly focused on the key performance indicator, the percentage change in the average risk score. Initially, the average risk score was at 3.17. After implementing new model recommendations, the score dropped to 2.72, which is a 16.32% reduction. So this highlighted that there was improvement in the model reduction across various projects. If you look at the pie chart, it summarizes the projects by outcome. Around 43% of the projects were successful, while the remaining were either partially successful or unsuccessful. If you look at the graph at the bottom, this is a risk difference between the original model dataset and the newly developed model dataset. The bar trend downwards into the negative axis. This clearly demonstrates that the risks has been reduced with the implementation of the newer models across various projects. This is the ML model recommendation system that we developed in order to find the most appropriate ML model based on the project characteristics. If we take an example of an AI category, AI healthcare category, followed by a project under that category, IBM Watson for oncology, with the click of a button, we'll be able to generate the top 3 recommended ML models for that particular project characteristics. One being deep Q network, conditional random field, neural radiance fields. And if you look at another example of a different category, AI energy management, and take a project LEAP, it will recommend a Gaussian mixture model, principal component analysis, and k nearest neighbors. So a brief outline on the work we did was basically data preparation, data synthesis, model recommendations, and risk evaluations. We curated our original data along with the ML model catalog dataset to better recommend the best ML model using the Jaccard coefficient and semantic boosting, as well as the risk scoring. We then utilized a CTGAN, a data synthetic model, to synthesize the data for handling the sparse data. And then we normalized the mass attributes, scope, components cost, and data volume. We then computed a 7-point Likert scale to assess the costs for both the original projects as well as the newly developed model projects. And we then finally developed a dashboard using Amazon QuickSights that clearly indicated the change in the percentage change in the risk score. Overall, there was a clear showcase on the reduction of the risks, which demonstrated that the better models, newly implemented models, worked well in reducing the risks associated with all the projects. This project can be redirected into different directions by integrating it with AWS services will enable us to real-time tracking of costs and data volume, enhancements to the data synthesis pipeline to better handling of the sparse data, and adjusting the mass pairs weights in real time will help us observe its impact on the model recommendations. Also, finally, we can leverage the time series forecasting for predicting the emerging risks in the future AI projects based on the previous historic patterns. Thank you. We are open to any questions.
Okay, team, I have one question online from June Huck, who says, I am not sure if I missed it, but I am not sure if the contents of the data and how it was gathered was shared. Could the team elaborate to the contents and origin of the data, as well as what quantifies as a successful or unsuccessful AI project according to the data set?
I can answer that. So the way we gather all the data is by basically we data scraped and we did our own research, because companies in general, they never disclose their costs or their processes or what models they use. So we ended up having to do manual research and also data scraping in order to gather the data required for our data set. And the next question was, sir?
That was, sorry. So could the team elaborate on to the contents and origin of the data, as well as what quantifies as a successful or unsuccessful AI project according to the data set?
While we since we have gathered a data set of projects, we also know which one of them have failed and which one of them have succeeded. So it's basically already in the data.
Okay. And Dr. Asmussen just had a comment, very impressive, with a tough subject with limited data.
Thank you.
And no questions in the audience?
I have one.
Oh, thank you, Dr. Baldo.
With respect to the MOS attributes, 3 of those are with respect to data. So it was very important, the data. Could you guys talk about that emphasis of data in the model, or the framework, I should say?
Oh, yes, of course. So essentially, in order to assess the risks, we have no public data available to us. So we were able to use a framework called MAS, which is also known as a multi-dimensional algorithm structure. And the way it worked is by, it emphasizes 6 spheres or 6 attributes, and each attributes have specific categories. Like in human in loop, they have to consider the categories such as direct, indirect, and auto. In direct category, we can say that there is direct human oversight, monitoring the model itself, compared to auto, which would mean that the model would be completely automatic without the intervention of any humans. And coming to algorithm function, we have several algorithmic functions such as descriptive, predictive, and assistive. And let's talk about data type. We have quite a lot of data types, but in our data set, we consider the text, image, audio, and geospatial. And data format, we have structured, unstructured, and semi-structured data. And let's also talk about the risks.
Okay, so actually, I understand this part. If you go down, there's some slides where you sort of summarized how this is impacted. Yeah, keep going. Keep going. Keep going. That one, nope. Back one. Another one. That one there. This risk scoring which caught my eye, where you made specific comments here about risk reduction.
Correct, sir.
Yeah. So I just noticed that 50% of that risk reduction was dealing with the data, and that's where I was driving with my question. This risk reduction, when you use these attributes, is really a lot of it is data, which makes a lot of sense to me. So I was trying to get some insights from you guys about that. That's what I meant.
So we had to score all the individual categories based on risk on a scale of 1 to 5, and that's what we did for each mass sphere. And also after that, we calculated a weighted equation, and we also had different weights for each of the spheres because they all obviously don't have the same weightage. And that is how we were able to obtain the overall risk score for each project using the mass attributes.
Okay, thank you.
Thank you.
Okay. All right, thank you, team. Okay, next up, Team Fractal Shadow. Please meet in the front, please.